Good afternoon. Today I will be telling you about remote sensing application to marine and atmospheric environment. So first of all, let us study about what a satellite sensor can measure. There are four basic parameters that a satellite sensor can measure, that is color and temperature of the feature, and slope and height of the surface, and roughness. These four parameters provide information about the surface characteristic. Just like color tells you about whether it is a vegetation, or coming to oceanographic use, whether the color of the water is blue or green, etc. Temperature tells you about the hotness and coldness of the object. Slope and height gives you whether the surface is in tilted shape or not. Later on, those things are utilized to find the ocean current, etc. And roughness indirectly tells you about the wind speed over the ocean. All these sensors we will discuss, and their applications one after another. So these are the overview of a satellite sensor, their wavelength range and utility. The visible and near infrared sensor, the wavelength range is comprised of 0.4 to 0.8 micrometer, and they provide information about ocean color and aerosol optical depth of atmosphere. And thermal infrared sensor, their wavelength range is 3 to 12 micrometer, and they provide information about surface temperature. And microwave, the wavelength range is 0.3 to 30 centimeters. They provide sea surface roughness information, slope and height information, and many atmospheric parameters. So coming to the ocean color, when we go inside the ocean and we see blue color of the ocean, and the blue color gradually changes into green color when we approach towards the coastal area. And if the water is not turbid, very transparent, we can see the ocean bottom features. So beginning of ocean color study started with Sir C.V. Raman's first paper on the molecular scattering of light in water and the color of the sea, which was published in the Proceedings of the Royal Society in 1922. So he explained the ocean color, that is following the Lord Rayleigh's scattering principle, which was applied to the atmospheric scattering phenomena, where Rayleigh has attempted to describe the color of the sky because the blue light is scattered more by the air molecules compared to other wavelength region, that is green and red. That's why color of the sky is blue in nature. And he attempted at the same time to describe the color of the ocean, but he has written that the much admired dark blue color of the deep sea has nothing to do with the color of the water, but is simply the blue color of the sky seen by reflection, which Sir C.V. Raman did not accept. And he explained the blue color of the ocean is due to scattering of the water molecules. So water molecules also scatter the blue light more compared to other wavelength region. That's why the color of the water is blue in nature. When we are going deep inside the ocean, we get pure seawater, and the color of the ocean appears crystal blue. So let us now study the absorption and backscattering characteristic of water, where we are seeing the absorption is very less which is represented by red line in the blue part of the spectrum, and slowly it is increasing towards the red end of the spectrum. And the reverse is the case of backscattering. Scattering is more in the blue part of the spectrum and gradually decreases towards the red. So both the absorption and scattering can be combined together to determine the reflectance of the water. When we are taking a satellite imagery in the red part of the spectrum, we can easily distinguish water and land, because water light will be absorbed most, so nothing will come out of the water to reach at the satellite sensor. So water color will appear very dark, and land will appear very white. So the wavelength range between red and infrared part are used to distinguish between water or find out the land water boundary. And this is the relationship between absorption, scattering, and reflection. And so reflectance is related to backscattering by absorption 0.33 BB by A. So you can see here the reflectance is high in blue end of the spectrum, and slowly it is going down to the red part of the spectrum. So this is the case of pure seawater reflection, and they are related to scattering and absorption characteristic of the water. So these are the substances changing the ocean color. Otherwise, ocean color is blue in nature, but when these substances present like phytoplankton, suspended sediments, and dissolved organic matter, if they are present in considerable quantity, then the color of the water will change. So now we will study about the phytoplankton. Phytoplankton, this slide shows you different phytoplankton species, and they have different shapes and sizes. And what they do, they absorb the solar radiation, and they utilize the photons for photosynthesis. And they are basically divided into two parts, that is diatoms, and next one is dinoflagellates. The diatoms, they consist of ornate siliceous cell-like cases, and the photosynthetic pigments are also present there. And when they decay, means they live for around 24 hours. After that, they die, and it will become a dead weight in the ocean, and slowly they will sink in the to the ocean bottom and form diatomaceous ooze. And then coccolithophores, they thrive in nutrient poor water, that is in open ocean water, where nutrient concentration is very less in the surface water, and they are covered with calcareous plates. And dinoflagellates, they have two thread-like structure. Some of them are responsible for harmful algal bloom, which is known as red tides. So coming to study the optical properties of phytoplankton, we can see the absorption coefficient, which is depicted in the green line, that is absorption is maximum at the 440 nanometer in the blue end of the spectrum, and slowly it is decreasing, and there is another absorption peak around 680 nanometer. And the scattering characteristics, they don't have a definite variation, and these two, absorption and backscattering characteristic, can be taken for different chlorophyll concentration to find out the reflectance spectra. So this is called biooptical development, biooptical algorithm development. So what it does, it takes the first phytoplankton and the colored dissolved organic matter and sediment which are present in the water, their absorption and backscattering characteristics are being studied, and later on it is related to radiance or reflectance, and when we will inverse the model, we can find out the concentration of phytoplankton or sediment, etc., which are present in the water. This whole process is called biooptical algorithm development. So in this case, we know that reflectance can be related to backscattering and absorption coefficient, that is R equal to 0.33 BB by A. So if you know backscattering and absorption coefficient of phytoplankton, and then if we will model that is from zero chlorophyll concentration water to chlorophyll concentration 5 milligram per meter cube, you are getting different reflectance spectra, and the spectra reflectance is decreasing at the blue end of the spectrum as chlorophyll concentration is going on increasing, but you are finding a hinge point around 550 nanometer. So this will be helpful to find out the phytoplankton concentration in the ocean water. So to find out the concentration of phytoplankton in the water, we take the ratio of two channels, that is reflectance of blue channel and the reflectance of green channel. So when we are taking a ratio, we get the pigment index. Going back, you can see the reflectance is changing here with changing chlorophyll concentration, but the reflectance at 550 nanometer is, though it is changing, but it is not as prominent as you are seeing in the blue end of the spectrum. So this gives a ratio which is known as pigment index, and that is lambda 1 is blue wavelength range, blue wavelength, and lambda 2 is the green wavelength, and you are relating to chlorophyll concentration with a means statistically, and you are finding out A and B, which are coefficients of regression. Then this algorithm can be applied to the satellite data to retrieve the phytoplankton concentration from the remotely sensed ocean color data. So now we will discuss about the ocean color data processing steps. So first we take the satellite data and do atmospheric correction, and then we retrieve the reflectance or radiance of the water. Then we apply the water quality algorithm what we have developed. Then let us discuss about the atmospheric correction part. The sunlight is passing through the atmosphere and penetrating into the ocean bottom, surface of the ocean water, and it is successively absorbed and scattered, and backscattered light goes passing again through the atmosphere and reaching the satellite sensor. This radiance which is coming out of water is known as water leaving radiance, LW. That is sunlight which is falling on the surface of the ocean. First, it is getting reflected from the surface, which is known as Fresnel's reflection coefficient, and remaining water will penetrate inside the water, and it will be successively absorbed and scattered by water molecules, and the backscattered light will reach the surface. Again, the specular reflection will take place in the water-air interface, and again the light will be refracted and will transmit through the atmosphere, which is known as LW. This LW contains information about the water quality parameters like phytoplankton, suspended sediment, dissolved organic matter, etc. So the atmospheric correction part will be helpful for retrieving the water leaving radiance from the total radiance received by the satellite sensor. So apart from the LW, the satellite sensor also records the scattered radiance that is coming out from the atmosphere, which is known as LR and LA. LR is related to Rayleigh component. LA is related to the aerosol scattered component. So to means total radiance received at the satellite sensor is LT, and if we will remove the LR and LA part from the total radiance, we can easily find out the LW. This LW, what we need, is known as water leaving radiance, and the process of subtraction of LR and LA from the total radiance received at the satellite sensor is known as atmospheric correction. And coming to the ocean color sensor, in OceanSat-2 we have ocean color monitor, and we have 8 bands, and these are the band centers, that is starting from 412, 443, 490, 510 and 555, 620, 740, 865 nanometer. This is first band is useful for determination of yellow substance and turbidity. Then 443, 490, 550 is useful for chlorophyll concentration, low chlorophyll, medium and high chlorophyll concentration. 555 nanometer helpful for acting as a hinge point for chlorophyll, and they are also helpful for determining the suspended sediment concentration. And the last 2 bands are near infrared bands, because near infrared bands the LW is 0. So whatever radiance that is coming and reaching at the satellite sensor is coming from the atmosphere. So these 2 channels are used for atmospheric correction. So this is the summary of application of visible remote sensing for monitoring the marine environment, that is seasonal mapping of phytoplankton, and detection and monitoring of phytoplankton blooms, then quantitative determination of suspended sediments, then ocean color, ocean and coastal circulation or surface currents that is derived from the ocean color information, and transport and fate of marine pollutants, oil slicks, etc., and estuarine, coral reef, and bathymetric study. So all this means things can be derived from the ocean color sensor. However, the ocean color sensors are depends on the resolution of the sensor. That is, if it is a high resolution data, then you can go for coral reef bathymetric study and some coastal feature study. Otherwise, if it is low resolution data of 1 kilometer and so, all other studies can be carried out. So this picture shows the phytoplankton bloom as seen by sea whips, and another ocean color sensor. You can see nice eddies, and it is in Barents Sea of Norwegian coast, and this is the Arabian Sea, and these are the phytoplankton bloom patches, and nicely captured by the ocean color data. And this left hand side of the image shows you the true color composite of the sea waves data, and without any correction. After doing the atmospheric correction, taking the pigment index and applying appropriate algorithms, the data is converted to map the phytoplankton concentration, and you can see different colors represents different concentration range, and it is starting through from blue to red end of the red color patches. The red and yellow color patches shows high chlorophyll concentration, and the blue and green color patches show the low concentration. And this is the Modis Terra Ocean product. That is, one product is water living radiance, LW, what we had earlier discussed, and then we have mapped chlorophyll concentration using appropriate chlorophyll retrieval algorithm, and then this product shows the aerosol optical depth over atmosphere. And these three products, water living radiance, can be used to derive not only chlorophyll concentration but also many geophysical parameters related to marine environment. And the chlorophyll is one of the product, and the byproduct is the aerosol optical depth. And coming to algal bloom, sometimes the you can find the high concentration of chlorophyll is present in the water. Even they are quite visible in the visible remote sensing domain, even without atmospheric correction. This can be detected by the ocean color sensor. And these red patches away from the coast, what you are seeing is the phytoplankton blooms. It was captured by IIRS P4 OCM data, that is OceanSat 1, which is known as trichodesmium, and it is observed near the Saurashtra coast during month of May. And this is the OceanSat 2 data of 20th February 2019. And this page, when you are doing simple image analysis, you can find out the bloom patches present here, and the extension of the bloom you can see in the satellite imagery after few radiometric enhancement, and you can identify it without doing any correction. So these phytoplankton blooms are highly toxic in nature. So we advise the fishermen not to go for fishing to this area, because the toxic substance will enter into the fishes, those who consume this phytoplankton, and later on this will enter into human health, human body. When human, they will consume the fishes. So during the bloom period, the fishermen normally avoid the fishing activity in this particular blooming area. And this is the ocean color sensor. It's detecting the oil slick patch, which is quite distinct in the coastal area. And this is the global climatology prepared from the ocean color data of sea weaves. And you can see the winter climatology, summer, spring, and autumn climatology, where you are seeing the blue patches near the open ocean area. These are the permanent desert areas of the ocean. And if the desert areas are increasing, that will indicate the intensity of climatic change, effect of climatic change. And this is the enhanced picture. This is the what I was telling you about the oceanic desert areas. And this is the summer climatology. And during that time, you are getting in the Arabian Sea, the monsoon wind is very active. So you are getting upwelling in this area, and the phytoplankton concentration is more here. And globally, you are seeing northern hemisphere, they get more sunlight, so they were rich in the nutrient content during the winter season, and now when they are getting sunlight, the phytoplankton concentration or productivity increases in the northern hemisphere. And this is the animation of 10 years CWIPS image, showing you the variation of chlorophyll concentration over the ocean and NDVI over the land from January to December. So, this same ocean color sensor of CWIPS captures the El Nino effect in 1 year, that is in January 1998, the El Nino year, and in July 98 you can see the reverse effect, La Nina effect, where the phytoplankton is getting depleted during El Nino effect, and rich chlorophyll you can find out in the La Nina period. And another utility of this phytoplankton map is to find out the productivity of the ocean. That is, you can find out daily column primary productivity. Suppose you have the chlorophyll concentration, that will give you the primary production, and you are integrating from surface to euphotic depth, and from sunset to the sunrise period, then you are getting the daily column primary productivity. So earlier we were using the dark and light bottle to find out the column primary productivity, and so different investigator in different period of time, they have estimated the average value of ocean productivity, that is starting from 2320 gigaton of carbon per year, and now the satellite data has provided the figure, which is around 45 gigaton of carbon per year. So now this is the picture of primary productivity, global primary productivity of the ocean, and the high productive area. It is showing the high productive area, and in the coastal waters, and the low productive area in the open ocean. And so you are getting daily images of primary productivity. So you can, it will be helpful for study of global carbon budget. So coming to remote sensing of the coastal waters. Coastal waters are optically complex water. What we have studied about ocean color is for the open ocean, which are optically very simple. So, but when we are entering into the coastal water, it is known as optically complex water, and because the backscattered light coming out of the ocean is from the bottom reflectance, and from the suspended sediment reflectance, and from the phytoplankton backscatter light, and if your vegetation like seagrass etc. is there, and their reflectance also will come into the satellite sensor. So to segregate each parameter in the coastal water, it is a very difficult task. So this is about the absorption and backscattering coefficient of suspended sediment. You are getting a U-shaped absorption coefficient curve, which is represented in dark line, and a convex backscattering coefficient curve. But it is measured in the waters of Paradip and Visakhapatnam. So these properties are normally site specific. You will not, means in different sites you will observe different types of curves. which may be exponential in nature. So now, if you can model the reflectance of the water with varying suspended sediment concentration, you may get this type of curves depending on reflection and absorption characteristic of the curve. So you can find out a suitable band and develop a algorithm to find out the quantify the suspended sediment concentration of the water. So this is 3 bands we have taken. For example, the reflectance a triangle is showing the reflectance of red band. Then the another channel that is around 600 nanometer, that is squares, and the circular dark dots are for green band, that is 550 nanometer. So the relationship is becoming non-linear when you are approaching the shorter wavelength, and it is becoming linear when you are approaching to longer wavelength. So based on that, you can formulate the algorithm whether it will be non-linear or linear. Similarly, we have taken IRS 1C WIPS data, and the red band we have taken, and that shows you the linear relationship with suspended sediment concentration. We have developed the algorithm synchronous to the satellite pass, and we have converted the WIPS image into suspended sediment concentration map. It is coastal waters of Paradip. It is a Paradip port, and this is Mahanadi River bringing out a lot of suspended sediment into the coast. And these are the suspended sediment concentration seen by the satellite sensor. So in the coastal waters, the presence of suspended sediment induces a strong backscattering. So the water means the satellite image receives the backscattering radiance, and their plume, etc., can be easily identified. This also tells you about the coastal circulation, etc., and their movement and sediment plume. These can be identified from the satellite image. And you can see this is the quantified suspended sediment concentration map during December 99, and it is March 2000. You can see the plume direction, and the vectors wind speed are from QuickSat data and superimposed on it. So it shows the suspended sediment plume is carried away along with the current. And when wind speed reverses and direction is changed, and the surface plumes, sediment plumes are carried out by the surface currents. But here you can see one plume going straight to the ocean. So this type of features will be highly useful to calibrate the numerical models of the ocean. And normally we think that the suspended sediment is confined to the coastal area, but these images show the suspended sediment are being carried out long away from the coast to middle of the bay. You can see. And these plumes, they carry a lot of suspended sediment, a lot of nutrients along with it to the open ocean. This will trigger the productivity of the ocean. So this is the 5-year climatology of the suspended sediment concentration of Kakinada coast from the OceanSat 2, and this is the climatology of prepared taking the data sets from OceanSat 2, and it is from January, February, March, April, and May, June, July, August is left out because of the cloud cover, because it is during the monsoon season. Normally this bay is full of cloud cover, so satellite data is full of cloud, so we have not taken it. And then October, November, December data are taken. And this is the phytoplankton concentration in the Bay of Bengal, prepared from Moody's data, another ocean color sensor. And this is from January to December. The chlorophyll concentration varies around the Bay of Bengal. Then we will come to understand the thermal remote sensing. The thermal remote sensing data can be used for study of climatology, global change in SST, weather prediction, gas exchange across the air-sea interface, dynamical oceanography, pollution studies. So it is simple that the emitted radiation will reach the satellite sensor. It is should not be mistaken as a reflectance. It is emitted radiation. Both day and night it reaches the satellite sensor. And if you have a thermal sensor, you can detect the radiance. If you know the radiance m lambda, and this is the Planck's equation, you can invert this Planck equation to get the temperature, because all other parameters are constant, and m lambda is detected by the satellite sensor. So the temperature of the object or sea surface temperature can be measured by the thermal sensor. So we have a thermal sensor in geostationary satellite Kalpana 1. So we are getting the sea surface temperature around the Indian Ocean region, Bay of Bengal and Arabian Sea. And this is the Moody's Terra data. They have also thermal sensors, and this is sea surface temperature generated by Moody's Terra, which is morning pass, and the corresponding Kalpana data. Just we have taken compared these two data sets. They are quite matching well. And this is the Kalpana data of afternoon pass, and this is Moody's Equa pass of 130 pass, and they are also matching nicely. So we have different ocean color thermal sensors, starting from NOAA, AVHRR, Moody's, and some geostationary satellite data. So this data can be used to study the marine environment. This is the sea surface temperature data from Moody's over Bay of Bengal. And as sun passes from south to north, you can see the water is getting warmed up, and in January and February, December, the North Bay is becoming cooler. And this is the winter climatology, summer, spring, autumn. It is prepared from the thermal sensor data present in the Moody's, and this is the enlarged view of winter climatology data, and this is the summer climatology data. And this data, ocean color data, as well as the thermal sensor data, can be used for detecting the potential fishing zones. So normally the phytoplankton is consumed by the zooplankton, and the zooplanktons are consumed by the fish. So this is called marine food chain, and the phytoplanktons are primary producers in the ocean. So if you can find out the high productive areas, then we can go there for finding out fishes. And this shows the different color of the water, which is indicating the color front, and different fronts of can be identified using the ocean color sensor, as well as you can identify also the thermal fronts, means dividing the water, means warm water to cold water. these fronts are considered productive zones, and we are extracting the features, that is the rings and eddies and fronts and meanders and the upwelling areas, which can be helpful for finding out the potential ground for fishing. So these are the zoomed out pictures of those features, and you can see the rings, coastal upwelling areas, and eddies, and the upwelling zones, etc. And easily you can find out the front, dividing the warm water and cold water, and this can be transmitted to the fisherman. You can take the ocean color data, and you can take the thermal data, ocean color data, and over the GIS platform we can find out the fronts, etc. So INCOIS, Indian National Ocean Center for Information Center, they are providing the potential fishing zone information to different state governments and NGOs, and later on these are transmitted to the fishing community. They go for fishing to those areas. And this is the enlarged view of the frontal areas that are being communicated. And this is the experimental study taking both ocean color data and the thermal sensor data. And it is found that when both the fronts are coinciding with each other, the productivity means fish catch is high there, and when they are not matching, it goes down. So now the Indian Council of Agriculture Research is also a part of this research activity. And this PFZ mission is comprised of the R&D and the modeling activity is being carried out by scientific organizations, and comprised of the satellite agencies as well as the fishing sector, and they generate the PFZ maps, and which are being transmitted to the fisherman community through maps, text, fax, phone, internet, email, electronic display boards, radio, etc. And the fishermen also go to fish to those areas, and they also give their feedback, and this feedback is highly useful and for fine tuning the algorithms. So this activity is being carried out all over Indian states, and the output is very encouraging. We have 67% success rate in potential fishing zone forecasting. Then the ocean color data is also useful for classification of coastal zone. So for this, high resolution data is required, and here we are showing the Minicoy lagoon. So we have taken the IIRS P6 list 4 data, and this is a supervised classified map of the lagoon, which shows beach sand, vegetation, seagrass and algae, open sea, lagoon, shallow area, and coral boulders, reef flats, and settlements, etc. And using the GIS and remote sensing data, we have classified the lagoon for pearl culture suitability. So we have identified a highly suitable site for pearl culture, where you can find a existing form of pearl culture. And these are underwater coral reef observations, and these are being the high resolution visible remote sensing data are utilized to map the coral reefs around the Andaman and Nicobar Islands. And now we will go to microwave remote sensing of the ocean, where we will study about passive microwave sensors, which are used for sea surface temperature, wind speed, and sea surface salinity retrieval. Then active microwave sensor, which are comprised of scatterometer, altimeter, and SAR, and where the scatterometer is used to find out the wind speed and wind direction over the ocean. The altimeter is used to find out the significant wave height, wind speed, sea surface height anomaly, geostrophic current, etc. And SAR is used for finding out the oil slicks, wave spectrum, coastal bathymetry. Now, this is the advanced microwave scanning radiometer for Earth observations, and you can see the sea surface temperature from the microwave sensor. The capability of microwave sensor is it can penetrate through clouds, where thermal sensors means thermal radiation. If you have a thermal sensor, if cloud patch is there, you cannot find out the sea surface temperature. But in presence of cloud, the microwave sensors will work better. So you can get the sea surface temperature in presence of cloud also. So this is the sea surface wind speed from MSRE data. And coming to the ocean salinity, you can see in the graph the sea surface for various sea surface temperature, and the brightness temperature at 1.43 gigahertz is varying as the salinity is also varying. So if now there are several satellites carrying the 1.43 gigahertz channel, microwave channel, and it finds out the surface salinity of the ocean. One such is SMOS. It is a European satellite, which is known as Soil Moisture and Ocean Salinity. This satellite was launched in November 2009, and it provides you the soil moisture information over land, and salinity information over the ocean. So this is the comparison between SMOS derived satellite derived salinity map, and this is the in situ measured conventionally by SIP's in situ measured salinity map. Both are almost matching, but some differences are there. And this is the Aquarius sensor, which was providing the satellite sea surface salinity information. You can see the Arabian Sea salinity is more, and the Bay of Bengal salinity is very less. So this is the another salinity map, SMAP. So now these salinity maps are used for many modeling processes of the globe. Then we will go to active microwave remote sensing. So first of all, we will concentrate on altimeter. It sends a pulse to the ground and measures the return pulse, and so it gives you height of the satellite from the sea surface. That is called range. And the height from the satellite orbit to the reference ellipsoid is called altitude. So altitude minus range will give you sea surface height. If you get two sea surface heights, then you can find out the slope of the water, and later on the slope will give you information about the geostrophic current. So now the backscattered shape of the backscattered radiation, backscattered light from the energy from the altimeter tells you the whether the sea surface is flat or roughened. Now this is the for a flat sea surface, you will get a flat backscattering, and later on, if you'll find sea surface is rough, then the shape also will change, and you will get a sloping waveform. So this information later on will be used to find out the significant wave height. So if you can relate the slope of the leading edge to the significant wave height, you will get the information about the sea state. So now this is a single echo of the altimeter, and you have to average the 1000 echoes to get a better shape, which can be interpreted easily. So this slope of the leading edge is related here for different significant wave heights from 9.29 meter to 2.75 meter. So you can see how it is. The slope is varying. So the slope of the leading edge is related to the significant wave height. Now this shows you the sloping sea surface and how it is related to the geostrophic current. Now this is the TOPEX Poseidon and Jason 1 radar altimeter data. The sea surface height elevation is in centimeters, and the bright patches are positive anomalies, and the cooler color shows the negative anomaly. And these are the information provided by the satellite sensor, that it gives you range. So the range minus the altitude, that is the height from the reference ellipsoid to the satellite, gives you the sea surface height. And this is the significant wave height determined from the shape of the return pulse, which is related to the leading edge. And sigma naught is the backscattered radiation, backscattered energy, which can be related later to the wind speed, etc. And this is sea surface height derived from altitude minus range information. And this slide shows you about the family of altimeter satellites. So the TOPEX Poseidon is a result between the cooperation of NASA and CNES, French Space Agency. Now we have with CNES and ISRO, they are combined together to manage this altimeter known as Altica. And apart from that, GOES 3, CSAT and GeoSat also carried the altimeters. And coming to Saral Altica, it is a project collaboration that is between France and India in the for this oceanic measurements. Altica is an innovative car-band altimeter system dedicated to accurate measurement of ocean topography. So it is also called coastal altimetry. So this is the sea surface anomaly expressed in meters from the Altica. And apart from that, the sea surface altimeter data along with the SST and chlorophyll can also be used for finding out potential fishing, potential grounds for tuna fishing particularly. So tuna, they are available in the low chlorophyll water, and where this the altimeter data is also used to find out the low chlorophyll water and low temperature water, and the means temperature around 20 means in our region 27 degrees centigrade, and a means suitable temperature range for tuna fishing, and the low chlorophyll water and the altimeter data all are used together to find out potential sites for tuna. And coming to the radar, when you are sending a pulse, if it is a house here and if it is a tree here, so first of all, the radar pulse will hit the house and get the return echo, and the later on it will hit the tree and get the return echo. So the time difference between the echoes will give you the distance between these two objects. This is the principle based on radar image, and the scatterometer sends a pulse and measures the return pulse. The so the return the backscattered means energy is related to the wind speed and wind direction, and so you have the it is a conical scanning scatterometer, and you have the sigma naught, and for different wind speed conditions you have and the backscattered energy, and that can be modeled to give the wind speed and wind direction. And this data is also available in the National Remote Sensing Center, the website means which is providing the data free of cost, and you can register yourself and find out the means get the data for further analysis. This is the scatterometer data, the one path around the globe, and this is the monitoring of two cyclones where the wind speed and wind direction is nicely depicted, and this is the snapshots of high resolution winds captured by SCATSAT during cyclone Varda in Bay of Bengal. And some of the oceanic wind speed products, etc., or sea state products are available in the MOSDAQ website. You can explore through it. Then coming to the synthetic aperture radar SAR, now we have the aperture of radar, which is artificially extended to allow for more data collection at a variety of resolution and swath widths. Now it is from 1 kilometer, means 1 meter to 50 meter resolution data is available from the synthetic aperture radar sensors. And this can be used to study the ocean wave spectra, and that is this is a theoretical simulated sinusoidal wave and corresponding wave spectrum, which is going in 45 degree, and the wavelength is 120 meter. So if you will plot it in polar coordinate, you will find out the spots, and which will show you the wind direction at 45 degree and the wavelength at 120 meters. Similarly, if you get real the SAR data, so similarly you can find out the wave direction and the wavelength, etc., and you can give an input to the numerical models. And apart from that, the SAR image can be used for bathymetric study, and if you have the two-dimensional model, hydrodynamic model, which can take information about the wind speed, etc., and the bathymetry to generate the sea surface roughness. So you can simulate the sea surface roughness. Later on, you can use this to simulate the SAR image. And when you have the real SAR image over the study area, you can compare both of them and you can find out the bathymetry from the simulation study. So it is called bathymetry assessment system, which consists of a suite of numerical models which calculate synthetic SAR image from a first Gauss bathymetry. The difference between the synthetic image and the actual image is minimized in such a way to generate a update of bathymetry. This process is repeated until the depth values converge. So this is the one of the application of BAS in the Belgian coast. So this shows you the bathymetry derived from the synthetic aperture radar data. And this is the bathymetry retrieved from RISAT data, and which is used the principle of the wave speed relationship, and wave dispersal equation can be used, and you can easily find out the bathymetry. But it should be where the bathymetry is gentle sloping, it can be nicely mapped using this principle, wave dispersion equation. And then comes the LiDAR data, and which simple principle, that is, it takes the speed of the light and find out the depth Z. So we have we can find out the water depth from the two LiDAR data, that is at infrared wavelength region, which is 1064 nanometer. Another is green wavelength region, that is 532 nanometer. So the infrared light will come from the surface, and the green light will penetrate deep into the surface. So the difference will give you the height of the water from the bottom. This will give you the bathymetry information, and this is the amplitude of return pulse and the time difference, and this is the underwater pinnacles. It is mapped by the LiDAR data. This is the sunken cargo vessel in the Baltic Sea, mapped by the LiDAR data, and this is the channel through the coral reef. And the maximum depth is which can be measured by LiDAR is 60 meters, and operating altitude is 400 meters, and scan width is 220 meters. And these are the challenges, that is small object detection and identification, sea floor classification, whether it is sea, mud, gravel, stone, etc., and land water discrimination. These are few channels. You can see the particular website to know more about the LiDAR. And coming to remote sensing of atmosphere, we can find out aerosol, optical depth, ozone concentration, water vapor, and weather information. So this is the optical depth of the atmosphere as defined by tau lambda. So if you know extinction coefficient and the atmospheric height from 0 to satellite height, you can find out the optical depth. So we have AOD image over the ocean. It's at 865 nanometer. We have compared the OCM-derived aerosol optical depth and CWIPS derived aerosol optical depth and MODIS optical depth. All three optical depths are compared, and these things can be used to model the atmosphere and the radiation budget of the atmosphere. This is the monthly average of aerosol optical thickness over the ocean and land as observed by the MODIS data. And you can see AOT over Indian region. It is going maximum in May, June, July, and minimum in the winter months. And this is the absorption cross section of ocean, and at the lower wavelength range, the absorption coefficient is depicted here compared to the visual wavelength, and this difference can be utilized to map the ocean. And there are several satellite from TOMS, GOMS, etc., which provide you the ozone concentration of the globe, which is expressed in Dobson units. And this is the June picture of ozone concentration, and this is the December. And you can see also Antarctic ozone hole in how it is varying from 2001 to 2009 from the satellite observation. Then these are ozone products are available in this website. You can explore further. And this is the atmospheric window, which is giving you information about absorption and transmittance, etc. These windows are used to find out the different atmospheric gas concentrations. And this is the carbon dioxide concentration of the globe, which is observed by orbiting carbon observatory to satellite, and giving you the atmospheric carbon dioxide concentration. And the same orbiting carbon observatory images. And another is MOPIT to monitor the monitor of pollution in the troposphere. And another chemistry transport model, the comparison shows you the carbon monoxide concentration. And this is the principle of retrieval of atmospheric water vapor, that over the ocean, which provides a uniform cold background due to the low emittance of water, atmospheric water vapor and cloud liquid water increase the brightness temperature measured by satellite-borne microwave radiometers. By exploiting two frequencies, that is 22 gigahertz and 31 gigahertz, we can easily find out the water vapor concentration. This is the water vapor concentration from MSRE data, and this is the monthly average water vapor concentration from the MODIS. And this is the average variation over Indian subcontinent. And apart from that, there are several geostationary satellites providing you information in the visual thermal data, and we get the meteorological information. And we have these products from INSAT 1D, outgoing long wave radiation, cloud motion vector, and AOD, etc. And this is the rainfall information and relative humidity and sea surface height, surge height information, and altimeter data. This is about the information about cyclone as observed by the geostationary satellites. And radar images also give you information about the water that logged areas after cyclone. Normally during cyclone period, it is covered by the cloud, so visible remote sensing data cannot be used. So during that time, radar sat data can give information about the flood effect in the coastal area. Coming to the megatropics, it is an Indo-French joint satellite mission for studying the water cycle and energy exchange in the tropics. So the main objective of this mission is to understand the life cycle of a convective system and that influence the tropical weather and climate, and their role in associated energy and moisture budget of the atmosphere in tropical region. So there are several sensors, Madras, Saphir, Scarab, Rosa, etc., which is giving you different constituents of the atmosphere. And these are some of the products from the megatropics. which can be utilized to understand the complicated tropical convective system. And finally, this is the cloud aerosol leader and infrared pathfinder satellite, which is giving you a three-dimensional information about the structure of the atmosphere, which is giving about information about cloud, aerosol, etc. And thank you very much.